Okay, well, hello everyone. My name is Daniel, and I just finished my third year in the PhD program at New Mexico State University. But today I'm going to be talking about my work in classification. In particular, I'm going to start with a project that I began in 2016, which was light curve classification. Now, those of us in the field, we know how challenging it is to do classification or modeling of light curves when the time series is sparsely sampled. So for example, this is a simulation that I ran using the Rubin opsim. So it uses Rubin cadence and Rubin noise. And the underlying model is you just cannot fit it. It is a microlensing event, point-like lens. And I have another example here of another gravitational lens, but this is not a point-like lens. This is actually a boson star model. But again, if you only had the points, this is in a single band, it would be impossible for you to fit it. So in the transient community, there is emphasis, great emphasis on identifying these transients early to enable follow-up so you can actually properly model the events once it concludes. So how do we go about doing light curve classification? So a lot of work by the community has been done over the past decades to derive feature engineering of robust statistical metrics that can be used to differentiate between different types of classes. And I just want to leave this up as a reference, including some popular Python packages that have compiled some of these. And my work, I started off with Rachel Streets, ATM Bachelet, and our collaborator Gautam Narayan, and we developed Microlia. There's a project that we published in 2019. And essentially what we did was I went through the literature and I compiled all the robust metrics that I could find to compute these statistics. And from here, we trained a tree-based model. We started with the random forest. We also included the XGBoost implementation. And in short, the program, what it does is you give a light curves, it computes a bunch of statistical features, and then it trains and optimizes the model. By optimizing, we mean selects the features that are most relevant, given the cadence of the light curves, and then it tunes the hyperparameters of the model. And we found in our work that adaptive cadence was very important, which is why you have to generate a training set. We include simulations, but if you're going to be training it, you want to make sure that the light curves you're training with are representative in terms of the cadence of what you're going to be ultimately doing the predictions on. So this is just an example of how you could implement the program. You can feed it your own light curves. You just give it a path to a directory that it expects the subdirectories to be the class labels, and it has to be in flux. So if your light curves are in magnitude, you set the convert flag to true, and you set a 0 point, it does the flux conversion. And once this gives you the training set, you call the ensemble model class, and the classifier class is actually what's going to optimize the model. You set this optimize equals true. If you have a lot of light curves, 10,000 light curves or more, this could take upwards of a day or two, but it's definitely worth it to optimize it, as I also show later in the talk. But this is the basis of the model. There's a bunch of other parameters. We have documentation that you can refer to. So again, if you have light curves, it's simple enough for you to just do these statistical metrics, allow you to even train a robust machine learning engine to start your project. And these are just some of the visualizations that we provide, including the confusion matrix. It shows you what are the most important features given the cadence. There are some features that are not relevant if you have very sparsely sampled data, but if you have a high cadence data set, then more features would be relevant. And there's a couple more, including t-SNE projections, ROC curves. But if there are any figures that you think should be added, I'm always happy to improve the program. So some tests that we ran recently was using the Elastic Data Challenge. On the bottom three classes, these are three different types of lenses, including single lens events, binary lenses. There's a lot of confusion between these. As far as the variables go, we have delta Scuti, R, Lyrae, eclipsing binaries, and Cepheids. The program does a relatively good job of differentiating between these, but there is confusion, and that's because I want to emphasize that the program, intentionally, I omitted period extraction. So I don't want to be extracting periods when I'm making new predictions, because we're only interested in finding lensing events. So for that reason, these statistics are computed very rapidly. There's no period fitting. There are no fit-based parameters. So in our case, we're only interested in lensing to follow them up early. So we combine these classes, and sure enough, we're able to, in principle, we'll be able to query Rubin data. And after this, I mean, you're still going to get much less than 1% from this. You would fit some sort of lensing model to determine exactly what is the lensing geometry of the object that you're following up. Okay. And what we found was very interesting was that actually we have early detection capabilities, despite the fact that we're training with full light curves. If we drip feed these are two events from the Elastic Data Challenge, lensing events, we find that in principle, we would have been able to pick up these events had they been going on live. So that's encouraging, which is not something I was expecting. But again, we're training with full light curves, and yeah, we can detect these light curves at very early epochs. So that's very encouraging. I also want to emphasize or highlight some work that's being done by Miguel Ramon and Juna Kroon at the University of Durham in the UK. They took microLEO, the program, and then they implemented their own model, sensing models of Boltzmann stars and these NFW subhalos. And they're very similar to lensing. So the rod curve shows AUCs of about 0.6 to 0.7. Reasonably well, but they use OGO2 timestamps. So they found in their work, yes, it's also very important to set the cadence. If you have a well-sampled light curve, these AUCs improve. That's not surprising. And they also find that the program calculates about 150 features. And they find that in this particular project using OGO2 timestamps, only about 25 prove relevance. So again, the program itself has a built-in feature selector, so we'll do this for you. Okay, but now we'll move on to beyond light curves. This is actually my PhD work. It's been with Maura Prescott at New Mexico State University. And we are interested in studying these high redshift Lyman alpha blobs. And these are giant reservoirs, 100 kiloparsecs across, of Lyman alpha emitting hydrogen gas. And we find these in protocluster environments and overdense regions. So the picture that we've been forming these are the progenitors of some of the largest structures in the universe, these large galaxy clusters. We find these on the nodes of the cosmic web. So we want to study these so we can understand how galactic evolution occurred at high redshifts and how the hierarchical structure of galaxies evolved from there. But the problem is these are extremely rare. How do we find these Lyman alpha blobs? They're very diffuse, they're extended emission. So for this case, we're not using light curves, we're using images. So we started with image segmentation, a very popular procedure in the community. Essentially, what we did is, this is blue broadband imaging. We only use one filter at this stage. We apply image segmentation, and I want to highlight the sigma threshold that we played with. Essentially, this is the standard deviation above the mean median background that a pixel must be in order to be part of the segmentation patch. And in our case, in this context of finding extended objects, we find that actually you want a low sigma threshold. And here I compare random forest versus XGBoost. I keep finding over and over that XGBoost tends to outperform random forest just barely. Sometimes they're neck and neck. But this was something that I've seen in the literature. XGBoost has picked up in popularity. Okay, so from this, we input 2 million objects with the trained XGBoost. And from these 2 million objects, we get back a couple 100,000. And this is something that I really want to highlight, is the fact that I've seen in papers projects where they say, well, we have this model, there's some random forest model, for example, and we try to optimize it, but the optimal models don't really show much improvement, so we're going to just go with the baseline. Default hyperparameters, use all the features, and I see this in practice, is the baseline models with all the features tend to give you the highest accuracies. So from the left, we have the base model, no optimization, and then from the middle one, the top 42 features only optimized model, and the right is the one here is the optimal features, or only the top 8 features, the optimal model. And yeah, in practice, the base model outperforms these other models, but the bottom panels, they show what happens when we input these 2 million objects. They have 10% are outputs, but for example, the model that only uses 8 features, there is no single detection that gives 100% probability prediction. And I don't know about you, but I don't want a model that gives back any candidate with 100% certainty. And that's what we see in these baseline models, is that actually, even though they may not be considered overfit, they are a little bit more overfit. So this is something that I emphasize, is definitely at least optimize number of features that you're using, because it reduces the overfitting of your final engine. Okay, but ultimately with this, we said, okay, let's use 8 features, because if we apply a 90% probability prediction threshold, the model that uses 8 features gives back 55,000, whereas the model that uses no optimization returns over 120,000. So it's poor performing in that sense. But still, 50,000 features is too much. This is like the GitHub picture of my mentor Gotham, which I just find very, very appropriate in many instances. But again, nobody's going to go through 55,000 objects. So we went to the next step, which is bringing in color information. So in this case, Lyman alpha blobs are characterized by flux excess in the blue that you don't see in the red. Some of you might be wondering, why didn't I just train a multi-band classifier to begin with? And that was because of the candidates. I had 1,000 candidates that were good in the blue, but only about 50 to 60 that were good in multiband. You can ask me about this later. But again, I have 50, 60 images, and I wanted to train a CNN, which is hard to do. I found that AlexNet, I want to emphasize, is a good model because it's very shallow. Only has 5 layers, been used in the past by GalmerNet to classify Sloan and by Toothless to classify radio galaxies. So easy to train. It still has a lot of parameters, but it's one of the shallower networks. So we trained it with multiband imaging. And actually what I found was that, yes, we can train it with blue and red, but when I add a third filter, the flux, basically a difference imaging, we find that this actually stabilizes the training. Now, in principle, a CNN trained long enough and deep enough would learn this behavior that, yes, your objects are bluer than they are redder. But in this case, with the limited sample sets, you're training these CNNs for less than 10 epochs. So we found that, yes, including this third filter in the training, very explicitly saying, hey, these are the characteristics that we want you to learn, actually stabilize the training. And with that, I want to show the optimizations. So we had a very exhaustive and complex optimization algorithm. And I just want to highlight the Optuna API, Python-based package that is extremely useful for optimizing hyperparameters. You can optimize anything. It's extremely flexible. And what we found was that the number of augmentations was among the most important parameters. And from these 50-ish images, my optimizer said, augment each of them, and we use 5-fold cross-validation, but augment each of them 23 times. So that gave us a positive sample size of 1,000 objects. So we were able to train a CNN with 1,000 in the positive class, 1,000 in the negative class. And that's something that I was very happy to see, but it was very difficult, right? How doing deep learning with 1,000 images in your positive class is very challenging. And I've seen this in the context of like the medical field, but I guess one of the speakers pretty more or less echoed this fact. It is possible to do deep learning with limited sets. Okay, so how did the CNN perform? We fed it these 55,000 objects and output 16,000. And sure enough, you see here in the left-hand image, from the candidates that were output, this is the area versus the color. So the objects that were output with highest probability were those that were bluer, which is a characteristic that we wanted to learn. We're happy to see that it learned it. Here we see 5 confirmed lemon alpha blobs in our sample, which were never seen by the CNN, not during training, not during validation. All 5 were output correctly. And from here, we said, okay, well, 16,000 is still too much. I'm not going to look at these by eye. I'm going to have to apply thresholds according to object parameters and morphology. So then we cut it according to the color, the area, and even the Gini coefficient and the probability prediction of the CNN. So even though all 5 confirmed blobs in our sample were correctly output by all of our machine learning models, ultimately only 3 made it through these morphological cuts. In the future, we hope to have a large enough sample set that these morphological cuts won't be necessary. But for now, we essentially recovered 3 out of 5. And with that, we have these top 3 candidates, which we're seeking follow-up with Gemini. So we know, these look, the bottom are the 3 that have been confirmed. The top are the ones that we have found from just visual inspection, the people that study lemon alpha blobs, me and my advisor. We think they look like what we were after, but we don't know. Is this lemon alpha emitting gas? Well, the spectroscopic follow-up will tell us. Okay, so with that, I just want to end with a new project that we're starting is we got proprietary data of several hundred lemon alpha blobs. So what we found was, yes, implementing our methods is only image segmentation, and we're using features like the ellipticity of the object and the parameter, the flux, image moments. We find that we trained on the left, we trained a classifier with redshift 3 blobs, and we find that the probability prediction is highest for the blobs that are more luminous, which is something that we expected, but we weren't able to show until now. And most important is we train with redshift 3 blobs, and we find them at redshift 2. So now we can span we can span and search a very large moving volume. Okay, so with that, this is the summary where essentially, yes, these statistical metrics are useful for differentiating light curves depending on the cadence. For image classification, I advise we start with image segmentation, extract morphological features, and ultimately go on to CNNs, which are a little bit less interpretable. But both of these programs have documentation. So